When a new LLM is released, I guess many of us often look at the benchmark scores first. And often we ask ourselves the question, how much does this actually mean, or what do these numbers really represent? So our next speaker, Florian Brand, is a research engineer at Prime Intellect, and he works on evaluating LLMs in different domains. And he will give us insights into evaluating these systems, especially in the times of agentic systems, and he will give us insights into what these scores actually mean. So we will, as usual, have time for questions after the talk, and if you join remotely, please feel free to put them in the Zoom chat. And with that, please join me in welcoming Florian Brand.
Yeah, thanks for having me. Also, thanks for inviting me. The interesting thing is that at every LLM release, some people look at one of the numbers or one of the headline results and then instantly dismiss it because they say, all right, all these evaluations, I don't really care about them because I am able to measure vibes. So I can use a prompt and the LLM then generates a picture of a pelican, of a ball game with a ball bouncing around, and that gives me so much insight that I instantly know how good this LLM is. However, that does not really work, and it's not really what evaluations are used for. Evaluations are used to measure and to put some number at a certain capability and to approximate the usage of said capabilities. The capabilities we cared about, or we still care about, changed over time, so I will go through the history and why we changed the things we measured. But in general, I think you can differentiate between things like knowledge, some narrow capabilities, for example, tool calling or long context capabilities. We care about things like coding, especially now that everyone uses Claude Code and Codex. We care about white-collar work, for example, accounting or law, or creative writing and role plays. So all these things are things we want to see how good our model performs so we can make an informed decision. And for all these things, we need to go through the history to know why we measured the things and how we ended up where we are right now. So in the early era of LLMs, so like 2020 to 2022, we mostly cared about evaluating the pre-training knowledge. So we used some questions which we found in the internet, then took some poor undergrads and let them annotate the data to see whether these questions are correct. And then we used this to see how good the model is at picking up the knowledge from the internet. For example, examples are MMLU or Truthful QA. And the questions always look similar. For example, this is a question from MMLU where the model is asked to calculate the GDP per capita over a span of years. And these are the things we mostly cared about, and the models got better and better and better. And the general setup for these evaluations was rather easy. We took the question, we threw it into an LLM, we looked at the answer by using a grader, and then we got the final score. And the final score is the thing we compared the models against. So there basically was no way to fuck it up, right? Well, we got creative with how we do things and how we have to do things. So for example, even the most simple example is that we changed a lot in the initial prompts. So we formatted the prompts differently, and that had an impact. Even simple things like adding new lines resulted in different scores. Or, as we have discovered relatively quickly, asking the model to think for some time before it needs to answer the question also impacted the result. So now we have one thing that we can change that directly influences our results and that makes the comparison between models or between these evaluation scores quite hard. The second component is the LLM. I mean, that's the static thing. So surely that is the thing that everyone agrees upon to use correctly, right? Well, even today, we have things like sampling parameters, and they have a huge impact. So basically what we do is that we can call the LLM, and we can change things like the temperature. And for some reason, even today, it has a huge impact. So here I used the biggest QAN model, the biggest open QAN model, just changed the temperature from 1 to 0.6, and it improved the score by 3% or 10% relatively. So I got a free performance boost by just changing the temperature to the recommended ones. And if you want to also have this free performance boost for your applications, you should look into things like the generation config for open models, or in the README or other documentations. And the last thing of our simple pipeline is the grading function, where we use things like regular expressions. Obviously, if we change our regular expression, or if our regular expression is bad, it might miss some correct answers and our score might be lower. Or we use things like a second LLM, which will be given the correct solution, and then is asked, all right, is this solution from the first LLM the correct solution? And obviously, this choice of the second LLM also has an impact on the final score, because a better model or a smarter model is able to differentiate between correct or incorrect. So this also impacts our final score. But over time, we didn't really care, or we cared less about things like general knowledge, and we wanted to see how good they are at reasoning. So we cared about the models combining their pre-training knowledge to answer harder and harder questions. That also meant that we weren't able to use our poor undergrad students, but now we got some access to some poor grad students and PhD, so we just took them to annotate our questions. And examples for these kind of evaluations are GPQA for chemistry and biology, or humanities last exam, or frontier math for math. And an example question from humanities last exam is a question: what the rarest noble gas on Earth as a percentage of all terrestrial matter was in a certain year. And the answer to this question is organoson. But some people looked into this question and found out that the answer is not a gas, it's not even noble, and it's not terrestrial. So HLE, which is a benchmark done by experts or by supposed experts, has a lot of errors, and a startup for chemistry looked into all the chemistry and biology questions and found out that 1/3 of the questions are wrong. For frontier math, which is like the hardest math benchmark out there, the organization behind that, who also used professors, PhD students, or PhDs, they also ran a checker, or they used AI to check all the solutions and found out that 1/3 of their problems likely have some invalid things or are likely wrong as well. So we are now in a state where, for these reasoning questions or for these reasoning benchmarks, we have a high error rate because it might be over the limit of what some humans think is the correct solution. And to go back to our our pipeline, because we scaled up the models, very harder to use. So we have to use an inference engine like VLM or SGLang, or we just call one of the APIs. And that will be a recurring theme. Of course, the choice of the engine or of your API has an impact on the results. So on the left side, we see that GPQA, which is an open model, was evaluated for their precision on tool calls, and some providers performed less than 50%. So basically, like half the calls were just badly formatted because they did some mistakes in their implementation of the model. So even if you used an API provider, you just got a worse model because you chose the wrong provider for that API. And on the right side, we see experiments that I've run on GPT-OSS, which is one of the most popular models, and I've run these experiments months after release through all the providers on Open Router. And the thing that we found out, and that shocked me if I'm being honest, is that some providers did not implement the reasoning effort correctly. So in this example, if you use GPT-OSS through Open Router on the AWS and you specified that you wanted a high reasoning effort, you got the model on medium reasoning effort. So even if you relied on AWS for this thing, you just got worse results because the provider fucked up. All these bugs are fixed nowadays, but it goes to show that relying on API might not be the end-all, be-all. So we are saying, all right, I just use my own GPUs, I use VLM or I use SGLang, but especially the inference engines at model release also have some mistakes. So for the GPQA model, they found out that only 20% of all tool calls were executed directly or correctly at the initial release. Another area of capabilities we tracked more and more because we started using LLMs more and more inside our products, for example, in RAG pipelines, is that we wanted to embed them in our products and call our tools, for example, web search or our internal search. And for this, they had obviously had to be able to call tools correctly. So we needed evaluations to reflect these capabilities. Examples are for tool calling SWE-bench, where we basically have the setup which we care about, and the customer support. We have the LLM that acts as a customer agent, and we have a second LLM which acts as a user, and the customer agent has to call tools to look up in the database what the correct things are or to resolve issues from the user. Or we have things like SWE-bench for instruction following, graph walks for these long for these long context problems. And the good thing about these evaluations is because they are so narrow and they only care about one very specific capability, is that we can create them programmatically or synthetically. So basically we can write short Python script or a larger Python script to create those evaluations, then give it a human pass to see which examples are valid or which examples are interesting, and then use that. And if we can create the evaluations synthetically, we can obviously also create the training environments synthetically as well. And that's what we did at Prime Intellect with General Agent as an example for these evaluations or for these synthetic environments. What we basically did is that we created a tool calling environment with over 4,000 tasks, and when the model needs to call tools at an increasing difficulty to solve the problems of a user. And we found out that training on these synthetic environments then improves the scores on tool calling benchmarks, for example, TauBench or BFCL and so on. So we can easily create the training data to solve the evaluations we also easily created. These days, the thing we mostly or maybe solely care about is automating work or helping us at work, which means obviously white-collar work. The poster child for this is coding, as everyone starts or is using Claude Code and code extensively. People write code less and less and use these models more and more, but also things like accounting, like law, like consulting. All these things are interesting to see how well models are able to do these tasks. So we also need to create evaluations for these tasks to see how well they are able to reflect it, which means we need to pay the worker in these professions a good amount of money, so the hourly rates, to create and annotate the data, which these days means that just the data annotation part for these more interesting evaluations are in the mid-5 or even mid-6 figures, and the trend is going up and not down, which is also really bad for academia because it means like academia can't create white-collar work-related evaluations because they are priced out to pay this amount of money just to create one evaluation for one paper. I think the most popular example for these evaluations is SWE-bench Verified, where the model is placed in a GitHub repository. It gets a real GitHub issue, and then it's tasked to solve that GitHub issue and see whether the tests passed after it has solved it. But we also have things like Terminal Bench, which is also coding related, with more broader tasks from solving bugs up until creating new things. Machine learning tasks are also in there. So it's more reflective of broader coding tasks. Or we have things like Apex agents and GDP-eval, which are broader for white-collar work, where the models have to create presentations to mimic consulting. They have to create defenses for legal work. They have to create spreadsheets and multi-sheet spreadsheets to calculate accounting. And all these things are are more and more closely resembling the real work of us humans and of us white-collar workers. And the new thing here is that these models are used in a product or more specific, a harness. The most popular harness is Claude Code. But that also means that for our evaluations, we need to reflect this reality. So we also need to include our harness into the stack to run these evaluations. And the harness is basically a set of tools. The tools are described by a prompt, different settings, things like compaction, the overall loop, how the model is called, and all these things define a harness. And also, for example, one of the more popular tools is to read a file, and all the harnesses have a bespoke tool to limit the output of this read file tool, so it does not clog up the agent by reading a wrong file, and you suddenly have tens of thousands of lines in your context, and you just bust the model. That's basically why we create harnesses in the first place, versus us just dropping it into Bash. Examples which everyone will probably know are things like codecs, like open code, like cloud code, cloud cowork, and so on. We have a plethora of these right now, and they are used extensively. It also means that we have the thing that we have seen in the talk previously, that these LLMs are increasingly trained in their own respective harness. So the latest GPT model is trained inside of codecs, so it knows the codecs tools really well, and it knows the codecs tools better than any of the alternatives. So if you use GPT inside of another harness, you might have different results or different experience because the model does not know or is placed into an environment where it has tools that it has never seen before. And the impact of this harness or the selection of this harness is the biggest impact in our whole pipeline. We looked into the SWE-bench Verified scores with the same model, so the problem or the evaluation is the same, the model is the same. The only thing that is changed is the harness, and we looked into different reported numbers. And for Kimi K2, we had 3 different harnesses. We had one from the US Center for AI Safety, and the model performed quite badly for that time. When we looked into the scores from Mini-SWE agent, which is from the benchmark providers themselves or creators themselves, it basically just places the model inside of Bash. And then we looked also into the reported score by Kimi themselves, and the difference was 15% from the lowest score to the developer reported score. And 15% on this benchmark basically means 6 or 9 months of model progress. So you can jump ahead like 2 generations of models by using the proper harness and using the model in the correct setup. Or you can use today's models and feel like it's summer 2025. Our harness obviously has to run somewhere on something, which means we place it in a sandbox, and the sandbox has to run on some physical hardware. And obviously, that means that the hardware that we have access to or that we used for these sandboxes has impacts on the final results as well. There are some benchmarks which require really specific hardware. For example, there's kernel bench where models are asked to create LLM kernels for NVIDIA GPUs, and for this you need the specific NVIDIA GPU because every NVIDIA GPU results or needs a different kernel. Or we have benchmarks like post-train bench where one model is asked to fine-tune a different model on one H100. And if you change the H100 to a B200, you can't compare the scores at all. So you need to have these specific things. But for many of the software engineering benchmarks or white-collar benchmarks, we basically get things like you need 2 CPU cores, 50 gigs of SSD, and 2 gigs of RAM or something, and that's it. So everyone kind of uses these settings, but these settings, these standardized settings, also have an impact on the overall result. Sometimes a model run a command which is resource intensive, which would then spike the resources of the sandbox and kill the sandbox in worst case. For example, if I run something which is really memory intensive, I only got 2 gigs of memory, the sandbox would get killed. But if we allow like these short bursts outside of our hardware requirements, we would get better results or less infrastructure errors. And there are other benchmarks like Terminal Bench 2, where each of the tasks is restricted by wall clock time. So each of the tasks has, for example, 10 minutes, some have 30 minutes, some have 4 hours. And these timeouts are dependent on your latency to the model provider. So if you are unlucky and call the Anthropic API at a bad time where everyone in the US is awake, you might have worse results because the model just takes longer to answer. Or if you have worse hardware where the sandbox runs, your commands take longer to execute, so the model has less time to observe the results and to improve its score. And someone ran GPT 5.2 and found out, or initially used the timeouts that the evaluation creators set, and their score of the higher reasoning effort was lower than the lower reasoning effort. So they increased the timeouts by 5 times, so basically gave the model enough time to solve the task. And afterwards, they had scores which reflected that models are at least on a similar capability level. So here we got a 15% increase in absolute terms by just giving the model more time or better hardware to execute, which also, again, influences our final number. So we have all these different components, and each of these components has some impact on the final number. Some of them have a way higher impact than others, but it also kind of means that you can't compare any score to any score run by someone else, because they have something changed in some way or capacity, and then you are out of luck. But also means either you need to run these things yourself, or you need to rely on one provider or one creator, which then runs the same benchmarks under the same settings every time. So you can at least compare these scores. And if you want to build benchmarks, or our current benchmark landscape has changed drastically over time, as we have seen. We started with a single LLM, which we called over an API, and now we are using LLMs with harnesses, so they became big systems. And if we look forward just a bit, we can see that things like OpenClaw or also the other harnesses have more and more things incorporated in them, with persistent files and users talking over days, weeks, or months with their AI system. And we need to reflect this reality as well. So we are moving more and more towards towards more complicated infrastructure, which needs to reflect the reality of people actually using these models. And our runtime for a single evaluation has also increased a lot. Like, these single general knowledge samples were done in a few seconds, and now for these coding benchmarks, we are running them over hours, and now going into the area of running them for days just to get one sample done. And that has created a lot of current and future problems for these systems. First is infrastructure. I think that should be clear by now that there are a lot of moving parts. The second thing is that the models are really clever to find ways around your setup, which is called cheating or reward hacking. So you need to find some ways to restrict the model. The biggest problem, where I will go into more detail, is that a lot of benchmarks are under-eliciting the capabilities, which means the benchmark creators don't work hard enough to really see what the models are capable of these days. And last but not least, is cost. The cost for creating benchmarks, as I've said, is now in the mid-5 to mid-6-figure range for some of these benchmarks, and running them, especially as more infrastructure is involved, is also exploding. So talking about cheating is the thing I've alluded to earlier, is that you have some setup and the agent loves to find some way around your setup to get to the solution faster, which is also known as reward hacking during training. Common techniques which we have observed is for coding-related benchmarks, for example, that some models found out that the Docker images the agents were placed in still had the Git history, so they just jumped into the future, found the commit that fixed the bug, then used this code, applied it, and solved the problem. Or some benchmarks use the open web to make it more realistic, and then have some block lists so the solutions aren't easily findable. HLE is one of the benchmarks where people move more and more towards tool usage, which means that they enable web access, and then they say, all right, I don't want to give the agents access to Hugging Face because the data set is hosted on Hugging Face, and that should be enough so that the agent isn't able to find the solutions. Unfortunately, there are a lot of third-party websites which basically rehost Hugging Face with a solution. Another thing I have seen more and more is that the agents found out how to embed the test results or the binaries of applications inside their code to pass the test results relatively quickly. Or that they found out how the test is run and on which hardware the test is run, and try to use this to abuse the properties of the underlying hardware. And common defenses is to remove everything that the agent does not necessarily need for the evaluation. So no access to Git, no access to the web, no access to weird third-party bash scripts and so on, and only restricted to the lowest set of tools that is needed. And the second, that is also something that we are seeing more and more, is that we use a second sandbox just for scoring the result, and we reset this sandbox and remove a lot of the things the agent has access to. And we can also use a second LLM to observe the first LLM and then say, all right, you are now cheating the benchmark, I stop the execution here. But obviously, because these things are now running for hours, means a lot of increased cost. Talking about under-elicitation, which I've said is the biggest problem for benchmarks right now, I want to give you two concrete examples. The first is ArcAGI3, which is this benchmark with different games, and it has multiple levels, so the LLM is placed into a level, has to figure out the mechanic, and has to apply this learning or these learnings to a second level, where maybe a new mechanic gets introduced, and then a third level, and so on. And it's a really hard benchmark, and the model creators of the benchmark creators of ArcAGI3 said that the official scoring does not allow for any harnesses, so just the raw model has to be used, because they found out that people will create some really weird and niche harnesses just to solve ArcAGI3, and that defeats the purpose of their benchmark. So what someone did on Twitter is that they used Codex and just gave it the problems with /goal, which in Codex just tells the model to continue until it finds the correct solution. And it ran over 12 hours, used hundreds of dollars in API costs, and it solved 61% of the public problems, whereas the official score for this model on Arc AGI 3 is 0%. So now we have 0% of the model versus 60% of the versus 60% when we use Codex. And another benchmark which is really new and up and coming, and the idea is something we have seen previously, is a benchmark called Program Bench, where a model has to explore and to re-implement an application. For this, the model is given as a binary, does not allow for any decompilation, and the model also has no access to the source code, and then is asked to replicate the binary or this program just like it does, basically to clone any application. The timeout, they restricted the model execution to 6 hours. So after 6 hours, the model is cut off. They use the mini SWE agent harness only, so no other harnesses. At least right now, they plan to use others as well. And they have a really minimal prompt, which basically says, all right, this is your task, and I want you to replicate it. And the model is then graded on automatically generated, but hidden test suite. So the model has to submit the application and does not get any insights to how far it is in its re-implementation. And the results are that basically no model is able to do anything. The result rate, by the way, means so scoring in this means that to get resolved or to resolve one of the tasks, you need to replicate the whole application and do 100% on all tests. So if you do 99%, it's not counted as solving it. We means people at Epoch, Meter, and I did a really small part in this, did a similar benchmark which we started a bit earlier, which is called mirror code. And mirror code is that the model has to explore and to re-implement a program. The program is given as a binary, there's no decompilation, and there's no source code access. But the big difference is that some of the test cases are given to the model, not all of them. So the model is not able to just replicate the test suite and create a lookup table. And the model is able to look or to run the test suite to check its results. And we don't impose any limits in terms of how long the model is able to run. And our results are that these kind of tasks are basically solved these days. So this is an application, I think it has 10,000 lines of code. And what we basically did is the more tokens we threw into the model, and we are now over 100 million tokens just for this one task, the model just kept climbing and climbing and climbing until it fully resolved. So basically our results were that these kind of things are possible right now, and it's only a question how much money you throw into these things. And speaking of money, if we were to do this for the whole task suite and with more models, just running the evaluation on its own would cost us over $100,000. So looking, or again, I think the biggest problem we have in the benchmarking space is that we are only able to make informed decisions based on what we measure, and that measurement has to has to look into the correct elicitation. So we need to use the models correctly and push them as hard as we can to answer questions like how well they are in offensive cybersecurity, or to answer questions like how big the gap is between open and closed models. Because only if we are able to answer these questions, we then can make informed decisions, which for cybersecurity means different things than answering the question or how wide the gap between open and closed models is. So if I want you to take one thing from this whole talk, is that you should use your models in evaluations to the maximum potential as just possible without spoiling the whole solution. With that, I thank you for listening.
Yeah, thank you so much for this great talk. I think that had many insights in it, and I'm sure we will have some questions from the audience.
Thanks for the amazing talk. Could you please show the plot again with the number of tokens in the x-axis and the performance? So, with the Opus 4.6, it's really interesting. There's a plateau for a very long time, actually, especially given this logarithmic plot, and then it jumps again. Why is that?
It's a good question. I think also that especially for re-implementation, you need to lay a lot of the groundwork first, and then you can, so if you implement one of the more broader things in an application, you then can easily clear a lot of tests at once, and that's one of the things we could see here. But yeah, that jump also surprised us.
Thank you.
Thanks for the amazing talk. I wanted to know if you have any thoughts on how one might go about evaluating a system like OpenClaw if one is interested in evaluating the memory or continual learning aspects of it.
Yeah, we are now the first OpenClaw related benchmarks, which basically starting to test these things. Basically means that you need to install OpenClaw, so you need to have the harness in place, and in terms of infrastructure, and in terms of design, the hard question, I think, is that you need to find out what you want to evaluate concretely. So if we are talking about memory, do you care about the stored memory in Markdown files, or do you want to probe your agent after 100 or 200 turns, whether it remembered some facts about you? And all these things mean a completely different setup in terms of the evaluation. So yeah, it depends on what you want to evaluate, and that can then inform your infrastructure.
I was wondering what your experience or what your current understanding is of tasks that are not easily verifiable. Like in the beginning, you mentioned, for example, law or accounting. As like for German law, it's quite difficult to have a verifiable answer.
So there is, for example, this white-collar work benchmark called Apex Agents, and they have law as one of the areas. And for this, they place the agent in a file system with a lot of different files, and these files are law, are related to the client. And then the model that is evaluated has to read all these files to come up with an answer. And this answer is then judged against a human-written answer or a human-written rubric with an LLM. So they took a lawyer and said, all right, for this problem, the LLM has to answer this thing, and this law. Or maybe a concrete number, and then they handcrafted a rubric by the lawyer.
But it does come down to, yeah, sure. But it does come down to an LLM as a judge approach rather than having, I don't know, like run a test suit that that actually proves a one-to-one correspondence.
Yeah, exactly. Because you need to have, like, the lawyer has to write the things and then the LLM as a judge. Because there is, like you said, there is no verifiable answer for law.
Regarding stuff like SWE-bench and so on, there was a blog post, I think, by OpenAI on SWE-bench Verified, which like kind of said, no, it's kind of a bad benchmark, at least at this point, because of like lots of tests being too specific. Do you just like, is this something you have to evaluate even for like early benchmarks, or do you like, is that something you only consider when it plateaus? Because I know like lots of new stuff is like automatically generated and so on, and there I feel like that danger would be even higher. For example, the program re-implementation thing is literally that, right? It's, please do it as specifically as possible.
I think you need to be at every stage in your evaluation creation. You need to check it at every stage. And for SWE-bench Verified, I also looked into the samples and wrote a blog post about them like 6 months or 8 months before OpenAI. And one of the problems is that some of the prompts were too ambiguous. But like that was one of the problems, and the other problem in terms of the general setup is that some of the tests were too strict, and that's why the benchmark later got killed or won't be evaluated anymore. And to solve the ambiguity problem is the thing that we are seeing more and more, is what SWE-bench Pro does, that I didn't like at the beginning. So SWE-bench Pro basically has the same setup as SWE-bench Verified with a human-written initial GitHub issue. And then they took another human who wrote a way longer issue description, which is more in depth. But then you can evaluate that the model actually solved these tasks and didn't have to guess what the tests might look like. So you need, I think a lot of evaluations right now need to be really specific in the things and in the initial prompts that they care the model to solve, to then evaluate it fairly against the setup.
Thank you for the interesting talk. So let's say I want to evaluate our LLM setup, which is like with a RAG-based approach that has like a lot of knowledge connected to it. So we don't have a benchmark in place because also like spending so much money on a benchmark is probably not something I can convince my boss of. But what I do have a lot is like the interaction of the users with the system. And can I somehow like generate valuable insights from the users interacting with the system and say like, okay, well, here we use this model and we used this part of the RAG-based system, and like from all of that I can gather like rough insights, or is this worth it? Or would you say like, no, like skip this, like you gotta do like really a benchmark?
No, I think it is almost better than like static benchmarks because you have live data. The big question is what you measure and how you are able to get these things. Like if you just have the raw interactions without any outcome, it of course is hard to judge what actually has an impact. So, but if you have, for example, the user doing like giving a thumbs up or down at those interactions would make it very easy, and from that you can also then bootstrap the evaluation.
Okay, I think we have time for one more final question. I think he was first.
Thank you. Do you have a recommendation for a benchmark for a relatively simple use case, just basically customer support on a knowledge base, so more or less RAG?
Yeah,
so
that's basically TauBench. TauBench is exactly this kind of thing, and now in their third iteration, they started adding that the model has to discover tools as it goes through the interaction with the user. And it is really hard. But yeah, TauBench is just what you've described, with a user or one LLM playing the user and another LLM having to search through a knowledge base.
Okay, so I guess Florian will be around a bit. If you have more questions, feel free to approach him. And let's thank him again for this great talk.